Okay, so let's continue our discussion of electromagnetic waves and gravity waves and the detection of gravity waves by the LIGO detector. Well, so we see how to generate both kinds of waves, and we know how to characterize them now by their polarizations. But how do you detect them? Okay, well, in the case of radiation, we certainly know how to do that. That's not very fancy. How do you detect a traveling electromagnetic wave? Well, from the traveling electromagnetic potential, you can make an E field and the B field and see what those physical forces do. Right? These affect E's and B's affect a charged particle through the Lorentz force law, and so I can look at that. Okay, so for my traveling wave, A was purely transverse, so my electric field just goes like the time derivative of A. Okay, A is a plane wave. It has a polarization, so E looks like this. I'm using a complex notation, so you might want to take the real part. It's fine. Okay, so I have this wave. It goes like epsilon. It inherits the polarization of the A field. It inherits the plane wave of the A field like that. Now my K is coming along the Z axis. Okay, and so in the dot product of K dot X, I have the time component and the Z component. The time component of the dot product goes like omega over C times CT. The spatial part goes like omega over C X Z with a minus sign for the Minkowski metric. And I see a traditional traveling wave. It depends upon Z minus the speed of the phase velocity of the wave times the time. Okay, and that's what I expect, and the kinematics just gives that to me. So the electric field passes a charged particle, which is initially at rest. The electric field oscillates back and forth sinusoidally. Okay, and so it experiences a force, and it moves back and forth, and I detect that as in a radiator, an antenna. And I detect the current that's flowing, and I listen to it. Okay. So that's easy. Now how do you detect a traveling gravity wave? Well, let's try the same thing. Okay. Now we discussed this conceptually. We know we're going to have a surprise here, but let's try the same old thing. Put down a particle at rest and have no forces on it, so it's freely falling. And let's have a gravity wave come and smack it. Okay, so here's its velocity. Okay, I'm writing it in the rest frame, why not? Okay, so C 0, 0, 0, like that. And its equation of motion follows, okay, it's a particle with mass. Okay, so it travels on a geodesic, and I write down the geodesic like that. It's initially at rest, so I can do these inner products here. Okay, the only contributions I get are from mu equals 0, nu equals 0. I put that in there, minus c squared. Okay, and then I have this component of the Christoffel symbol to write down. I write that down. Okay, now my wave is weak, so I'm using linear gravity to do that. So I raise the index to eta with the Minkowski metric, and everything else is just this collection of H's. Okay, well, now what do I know? Well, I know that I have a traveling wave coming in, and I know that the only components that are different from 0 are H11, H22, and H12 are different from 0. But look, these components here all have a time component on them, so the right-hand side is 0. Okay, so I conclude, okay, that the time rate of change of the particle is equal to 0. It does not experience the gravity waves. Okay, so the particle does not move relative to the coordinates. Okay, we've argued this point before. Remember, I can't detect gravitation of any form if I just look at one point, because I can always jump to a locally inertial frame, okay, where gravity disappears, at least at that point, right? I jump out the window, and in that frame, And then in that falling frame, of course, everything falls at the same rate as gravity has been transformed away, and so I can't detect the wave that way. I can't detect the gravitational field that way. God help me when I hit the deck below, but that's a different story. Okay. So this is just an example of the equivalence principle discussion we had before. And when we had that discussion, we thought of a way around it. You're just looking at one point. Don't look at one point. Gravity waves provide stress, tidal forces. Okay, so they grab, they squeeze, or they stretch. So you have to look at several points, or 2 points at least, and see if they squeeze and stretch, because gravity waves transport stress, curvature, which is stress. Okay, so that's what we want to do. Sometimes it's nice to have a little analogy to understand that you can't observe the gravity wave just by looking at a single point. So I think of an analogy that occurs in that every mariner knows about. Okay, if you're a mariner and you're sailing your boat in the Bay of Cape Cod, okay, then you have buoys around to tell you what your course is, and the buoys might be free floating. They play the role of the coordinate. And I have a boat that's like the test particle in the ocean. Well, as a way, so I might have a boat number one over here and a boat number two over here, and they're right next to buoys. Okay. So their coordinates are given by the position of the buoy. Okay. Now a wave moves in, and what happens? Well, the wave pushes both the two body systems, the boat and its buoy, over here, the same way. So the coordinates don't change, but of course the physical distance does change. More space-time comes in between the boats. More wave comes in between the boats, and they move apart. Maybe more wave leaves, more space-time leaves in the case of gravity, and so the objects come together. But the coordinates and my test particle are in the same consistent dynamical system, and they move in a synchronous fashion. Okay, so clearly I can measure the distance. I have to look at a geometric quantity to measure the distance between the boats. Okay, and so that will be provided by my geodesic deviation. Okay. So we need two particles to detect the gravity wave. Okay, so I'll call chi a spatial 4-vector like that. Okay, and it'll be the constant position of a test particle, and I'll let chi be the coordinate difference between two test particles. Okay. And then I'll ask myself, what's the physical distance between them? Well, the physical distance between these test particles, and only spatial components contributing, will be given by L squared, okay, equals minus the metric, spatial part of the metric, chi times chi. Okay, that's the physical distance, and I'm just reading that off our metric element, ds squared. I usually write it, but here I'm just writing it in this fashion for a three-dimensional application. Okay, but here's Gij. Okay, that's the metric in the x, y, and z direction. It's delta minus Hij for this application. Okay, and so I see that's where L squared picks up time dependence and spatial dependence. See, the chi's don't change. The chi's don't change at all. What changes as the wave comes by is h. H is a sinusoidal varying function. Okay, and I have components 1, 1, 2, 2, and 1, 2, which contribute there. Okay, so the physical distance changes, although the coordinate differences remain the same. Just emphasizing the meaning of the metric that we've been studying, and I think this helps a lot. Okay, now some people like to write this in a different fashion. They might like to write the metric as a Euclidean metric, Kronecker symbol Ij. Okay, and then I'll get the same formula if I do then put some dependence into the positions chi I. So these are not following the buoy anymore. These are contrived variables, so that I can write L squared is equal to Euclidean metric times chi I, chi j, and then and then if chi are related to the other spatial variables with a explicit h, then to first order, this expression is the expression on the other page. Okay. This expression you might find handier because Kronecker symbol is the simplest. It's a good old Euclidean geometry. That might be a preferable way for you to think about it, rather than thinking of the geometry changing, okay, and the positions being held the same. Here the positions are changing, but the geometry is being held the same. To first order, it's just a matter of organizing the definitions appropriately. So now I can suppose that a gravity wave approaches, okay, so here's h mu nu. I have, okay, and each, okay, and the wave has sinusoidal dependence. So I've written down cosine of k dot x instead of e to the I k dot x because I want to just emphasize real parts. Okay, but here's the gravity wave coming in. It's in a polarization state A. Okay, that's called a plus polarization state, B being the cross polarization state, and I've written it down here. Cosine of k dot x is cosine of k, x0 minus x3. x0 is ct, x3 is I've been usually calling that, okay, z. Okay. Well, however we like to set that up. In this particular case, therefore, chi, the distance in using this notation is I see chi I, I'm writing it out in three-component form, has chi 1 in this element, chi 2 in this element, and nothing in the direction of propagation. It's transverse wave. Okay, that's the initial, and then I have a half, okay, a half chi I k, okay, one of the indices is up, so there's a minus sign, okay, and then it's contracted against chi, and so I have a chi 1, okay, and I have a minus chi 2, okay. I have a minus sign, right? Because h is traceless, so h11 is minus h22. Remember, when I wrote down the polarization, I had an entry along the diagonal of a and minus a, okay, and so that's this minus sign over here. Okay, so now I can take a look at that pattern. So I can imagine how it looks as my gravity wave comes into the system. Okay, and so here I imagine starting off with the x's with mass points on a circle, and then I measure my chi relative to a mass point in the middle. Okay, and so what do I see? I see displacement in the one direction, okay, and then I see displacement in the two direction, but with the different signs. Okay, so if I get squeezing in one direction, I see squeezing in the chi 1 direction, then I'll have stretching in the chi 2 direction, like that. Okay, that's what happens when the phase of the cosine is equal to 0. Okay, and this is 1. Okay. Then I go to a phase where this phase is pi over 2, so the cosine goes away, and I'm back to the circle. Okay, and then I go to 3 pi over 2, and the cosine has flipped its sign. Okay, so where I had stretching, I now have squeezing, and where I had squeezing, I now have stretching. Okay, and so that's my picture of this formula as shown on this coordinate system, right, like that, for as a function of time at a position. Let's say x3 is 0, so time is going by, so I'm looking at different snapshots of this traveling wave. Okay, and then similarly for the other polarization, you'll do the same exercise. You have off diagonal term there, and you'll see that it's the same as this, except it's rotated by 45 degrees. So you'll just take these guys, rotate them by 45 degrees, and you'll recognize these as quadrupole moment oscillations like we found for tidal forces, right? We're seeing tidal forces here. We're seeing the same spatial stretching and squeezing that we found in the quadrupole moments of tidal forces and elsewhere in gravity waves. Okay, so I think that's how it works, and that's how the formalism works. Okay, and I think it's very, very clean and very nice. Okay. Okay, and here's my ocean analogy. I've already said that. Enough about that. Okay. So now we know that the arms of LIGO are going to change their physical length as the gravity wave comes by. Okay, and so let's imagine they're coming by. Okay, so I call the traveling wave epsilon of x, and then the metric for the plus polarization case. Remember, I have squeezing in one direction and I have stretching in the other direction. Okay, and so I've aligned my x and y axes appropriately in the case of the plus polarization. Okay, right? You see, I'm getting a squeezing in ds squared, the physical separation in the x direction, and a spreading for positive epsilon in the y direction. So I'm just including in here, okay, I'm just writing this as, you know, as g is equal to eta plus h, and I'm just putting in h by hand. Okay, I'm doing it for the plus polarization here to capture that particular case. I can also do the cross case, the cross polarization case. In that case, h12 is the same as h21. It's off diagonal, and so my metric changes with a coupling between the x direction and the y direction, with a magnitude of twice epsilon and a gradient. Okay, so that's how my metric will. I'm going to be using the plus polarization to illustrate, but that's fine. Either way you like to go. Let's do it that way, and that's how it happens. And I've illustrated it for the case where I have a source far away, a binary down here, and very far away in the z direction, I have LIGO, which makes measurements with one arm in the x direction and the other arm in the y direction. Okay, and stretching in one direction and squeezing in the other direction with this epsilon, and epsilon is the traveling wave. Okay. Okay. So the length of the arms in the LIGO detector are each about 4,000 meters long. The wavelength of gravity, okay, well, it's just the wavelength, it's just its speed divided by its frequency. Its speed is the speed of light. Its frequency, well, the frequencies we're interested in on the order of 100 cycles per second. So I put that in here. I see that the wavelength is on the order of 1,000,000 meters. Okay, okay. So I can treat epsilon as a constant over the detector. Okay, its wavelength is much larger than the size of the detector. So I don't have wiggles inside the detector. I just have a constant epsilon across the detector, and that makes life easy, doesn't it? Okay, so as the gravity wave passes, the physical lengths of LIGO's arms change. If I go back to the previous screen, okay, and I look and I take the appropriate square roots to get the physical lengths, delta x arm, in terms of the coordinate changes and the metric, I have this in the x direction, taking the square root, the 1 plus epsilon because of 1 plus epsilon over 2. Similarly in the y direction, but of course with a minus here. Therefore, the time difference for light traveling to and fro along the two arms is the difference. Okay, so I take the difference, so they both sum. Okay, and then I have the length to and fro, so it's 2L divided by C to get the time. Okay, and so I see the change in time for the arms. The time difference for light to travel to and fro is given by this expression. Okay, and then if I make n trips, like I do in the experiment, n's on the order of 100, say, I can make a powerful laser to maintain coherence and okay, and for that length of duration, and then my change in the arm length will be like that. Okay, and that's what I have to measure. That goes into the interferometer. I want this to be a fraction of the wavelength, so I can get an interference pattern when a wave comes in or goes out, and I can notice a difference across the object like that. Okay. So our next task is to consider the source of gravity wave, okay, instead of the gravity wave itself. And so we'll model that, okay, discuss the generation of the gravity wave, and let's do that next time.